All right. Hello, everybody. Thank you guys all for joining. My name is Nick. I'm a senior product manager here at Deepgram. I primarily work on the speech to text side of our product lines. Later on, you'll hear from Jack Kearney, who is one of our staff research scientists here and played a major role in the product that we're going to go in depth about today, which is Flux, our first and really the world's first real-time conversational speech recognition model designed for voice agents. So before we get started, a couple of housekeeping items. If you guys do have questions, please go ahead and put those in the Q&A section. We'll go ahead and answer those as this is ongoing, but we'll also have about 15-20 minutes at the end to go through questions. And I believe we also have a couple of polls that we'll be sending out in chat throughout this conversation or throughout this webinar. Feel free to answer those. We'll post results as we're going through this. And with that, I think we can go ahead and get started. So for those of you who may or may not know Deepgram, Deepgram does voice AI. We started a very long time ago now on building out speech-to-text transcription products. We have since built out a slew of different voice AI products, including a state-of-the-art text-to-speech model and a voice agent API, which ties all of those components together in an easy-to-use API for developing voice agents. So I am going to go ahead and start talking about our newest product, Flux, which is a speech-to-text, a real-time speech-to-text product. Like I mentioned, designed specifically for voice agents. I'll go through kind of the background of the problems we were looking to solve with Flux, and then I'll share a couple demos, a little bit around API design and some benchmarks, and then I will go ahead and pass it off to Jack later on, who will go through some of the more technical details and research background of the Flux model. So let's go ahead and get into it. So one of the things that we've been observing across the industry for some time now is really everything is moving towards this real-time paradigm, this real-time interactive paradigm. And existing speech-to-text, streaming speech-to-text solutions really weren't designed for this. They weren't designed for even real-time, but they especially weren't designed for real-time interactive voice AI applications. And so you end up with these traditional speech recognition models that were designed for caption-like transcription and not for conversation. So this leads to complex challenges and trade-offs when you're developing a voice agent. So on the one hand, you're looking to achieve ultra-low latency. So a natural conversational agent requires sub-second response latency, and that includes your entire pipeline of speech to text, your VAD or turn detection solution, your LLM and any tool calls, and any additional network latency that you end up incurring on top. All of that is balanced with the other side of the problem, which is the interruption problem. So knowing exactly when a speaker is done speaking, not interrupting too soon, but interrupting or responding at the right point when the user is done speaking, and doing that in a way that achieves latency and does not interrupt. And all of this within your entire complex voice AI pipeline. So you've already got complex logic for managing turns, interruptions, context, transcripts, tool calls, what have you, and you're balancing these very challenging problems. And so these critical challenges and limitations with the current solutions out there end up leading to voice agents that jump too early, they interrupt users mid-sentence while they've paused, or they wait too long and result in robotic pauses that tell you that you're talking to a robot. So we set out to solve that problem a couple of years ago. And at the beginning of this month, October 2nd, we launched Flux, which is the world's first conversational speech recognition model. I will start with a demo video, our launch demo video that we did comparing real-time or OpenAI real-time's voice agent against 11 Labs voice agent against a voice agent built on top of Flux. And I'll play that, and then we can get into some more of the details around what is great about Flux.
Ever feel like talking to AI is harder than talking to a human? It's either constantly interrupting you. Hi, my 6-digit medical ID number is 341.
Please share the remaining 3 digits of your medical ID number.
Or it takes forever to reply. My 6-digit medical ID number is 341246.
I'm glad you reached out. I can't access or store personal medical ID numbers.
That's why Deepgram built Flux. Flux goes beyond ASR. It's the world's first conversational speech recognition model. My 6-digit medical ID number is 341 246.
Sure, I'm here to help with any questions about medications or anything else you might need.
Yeah, is my prescription for doxycycline ready for pickup?
Yes, your prescription for doxycycline is ready for pickup.
Natural sounding conversations, no unwanted interruptions. If you're building a voice agent, make sure it's powered by Flux.
So that is the Flux demo within a voice agent scenario, and that's really the impact of this product that we've developed. Of course, it is just a standalone speech-to-text, conversational speech-to-text product, but when building a voice agent, it really does have these incredibly meaningful impacts. And so Flux is the first speech recognition model that's designed not only to be streaming first, which the current streaming speech-to-text models on the market were never designed to be streaming first. That was always shoehorned in later. So it's designed not only to be streaming first, but it's also designed to be conversation first. So Flux, the first conversational speech recognition model designed specifically for real-time voice agents. Flux comes with model integrated turn detection. So turn detection that understands full turn audio and semantic context, far beyond simple VAD or semantic-based solutions that you might be using or familiar with. It's a single API that replaces your speech-to-text solution and your existing turn detection alternatives without the added latency of a separate turn detection model or the addition of complex custom logic that ends up being faulty anyhow. It comes with ultra-low latency, so you can expect transcript updates about every quarter second and around sub 300 millisecond end of turn detection, full with complete turn transcripts. And all of that comes with the accuracy of Nova 3. It also comes with customizable turn taking dynamics. So you can configure your turn confidence thresholds and your turn timeout thresholds specifically to optimize for your use case and your voice AI pipeline. It also comes with, and I'll get into more detail about this in the API design later on, but it also comes with out-of-the-box conversational cues. So instead of just sending you transcripts, Flux will send you conversational events and state change events. For example, start of turn. So start of turn means that the speaker has started speaking for the first time in their turn. And if your agent's currently speaking, trigger your barge in logic, interrupt that agent. And then I'll go into more detail about eager end of turn, turn resumed. And then of course, end of turn is the event that signifies full end of turn. But really these events tell your agent exactly when it should be listening, when it should be thinking, and when it should be responding. And now I will go ahead and share a demo. Give me one sec. All right. So what you're seeing here is a demo comparison. This is also available on flux.deepgram.com. It's a demo comparison of Nova 3 and Flux. So Nova 3 is on the right, Flux is on the left, and I will go ahead and connect. And so as you can see, as I start speaking, you'll see Nova 3 transcribing and interim results here. And as those interim results finalize, you'll see the transcript move up here into the green. But what you'll see with Flux is a little bit different. Flux will be maintaining this transcript, the entire turn transcript, and on an ongoing basis, it is calculating this end of turn probability. And when I finally do finish speaking for my turn, you'll see this transcript finalize and move up in the UI. And that's the power of Flux. One of the examples that I like to show here too is going through a phone number. So my phone number is 847 487 7392. And yeah, that's Flux. So definitely go to flux.deepgram.com and try this out. But yeah, you'll see that this is a very different paradigm from what you're used to with Nova 3 and with other speech recognition or streaming speech recognition products, in that we manage this entire turn transcript for you. We send you these conversational cue events. Right now, it's just showing updating. That's updating as about every quarter second as I continue to speak. And I will talk through the other events back in the slide deck. All right. So as I mentioned earlier with the conversational queue events, Flux is really based on a state machine that's designed to make your voice AI development simple. So, oops. So these are the always on events. These are the ones that you're observing in that version of the demo that I shared. So update events will send you about every quarter second. This just means that we've transcribed more audio, but the turn state hasn't changed. The transcript may have updated, it may not have updated, but you'll get these about every quarter second. The start of turn event means that the user has started speaking for the first time in their turn. So if your agent is currently speaking, you want to trigger that barge in logic. Otherwise, you know that the user just started speaking for their turn and now they're currently speaking. So we've now moved from this initial state to this turn ongoing state. And then the final critical event here is end of turn. So this means that the user has finished speaking for their turn and your EOT confidence threshold is configurable. The default is 0.7, but it is configurable. And so when you receive this event, you want to fire off your agent reply. And then down here, I'll talk about the speculative generation events. So speculative generation really is a concept on kind of the cutting edge of voice AI today, which means that we want to shave off end-to-end voice agent latency by pre-processing LLM responses, agent replies before we're sure that the customer is actually done speaking. And so we've built this into the API design. So when you configure your eager end of turn threshold, which you'll want to be less than your end of turn threshold, we will send you an eager end of turn event, which means we are moderately confident that the user has finished speaking for their turn. And at this point, begin eagerly preparing that agent reply and await that end of turn event. And when you do get that end of turn event, you want to fire off that response that you've already been pre-preparing. In the case that it wasn't actually end of turn, we'll send you this turn resumed event. And this means that we thought that the turn was about to end or the turn ended, but it didn't. It was a pause or false positive end of turn, and the user continued speaking for their turn. So we'll send you this event, and in that case, throw out your pre-processed reply and begin awaiting eager end of turn again. And so this allows you to configure the trade-off between additional LLM calls with reducing end-to-end agent latency. And here's just a quick example of a life cycle here and some of the values that you'll get in each of these turn info events. So on the left, you've got start of turn. You've got, for each of these turn info events, you'll get turn index. You'll get audio window start and audio window end, which is the amount of audio that we've been processing for the turn. The transcript, which is the full turn transcript. You'll get this words array, each word with a word confidence. And then you'll get, on an ongoing basis, these end of turn confidences. And so you can see start of turn, eager end of turn, turn resumed, and then you would have gotten eager end of turn again before you got end of turn here. And now I wanted to show some of the benchmarks that we did for Flux. So on the left here, you can see precision. In the middle, it's F1, and on the right, it's recall. So you guys are hopefully familiar with some of these alternative solutions. The one you're probably most familiar with is Celeravad. And so Celeravad is these purple dots here. And really, Celeravad it's a solid voice activity detector, but it really isn't smart at all about detecting end of turn. And so the precision is super low for Celeravad. But what you will see is, of course, the recall is high because if I'm choosing a small VAD timeout, I'm going to think it's end of turn all the time, and it's going to be a false end of turn. And that's when you'll get those interruptions, interrupting the user while they're speaking. And then the other models here that we've benchmarked, Assembly AI's universal streaming, which is really intelligent endpointing, not really a true turn detection model. We've done LiveKit end of utterance in the green here. We've got Pipecast Smart Turn and Crisp turn taking in the pink. It's a little bit hard to see, but as you can see, Flux is on the top left of all these charts, and it achieves ultra low latency, ultra high precision end of turn detection. And this is possible because of the model architecture that combines the context of a full turn speech to text with your turn detection solution. And so the context that the model has to calculate these end of turns is much more vast than the context that some of these other models have. And you're not stitching these things together in a way that incurs additional latency. And all of this comes with the accuracy of Nova 3. So here we've just got a comparison of Nova 3 versus Flux, median word recall rate, overall word recall rate, recognition rate, sorry. I did want to mention that we do have a lot more benchmarks that we have linked in the resources tab of this platform. So you can go ahead and look at the blog post. And we have a number of research blogs that we published as well around Flux that you guys can go ahead and take a look at. I think we can go ahead and link those here too. But that's all I've got. And now I'll pass it off to Jack to talk more about the technical and research side.
Great. Thank you very much. All right. Let me get my share working. All right. That looks good. All right. Hi, everyone. My name's Jack, and I am a staff research scientist here at Deepgram. And as Nick was kind enough to mention, I had a significant role in the development of Flux. And we're really excited to kind of share some of the technical details of that with you. So I'm going to dive straight in. You're putting some really good questions in the Q&A. Hopefully we'll be able to get to most of those at the end. And I think I'm going to answer some of them in my material, so pay attention. Okay, so goals for Flux. Nick kind of mentioned, what Flux is supposed to do. It's supposed to be SET designed for conversation. And so I want to kind of like translate that into what we were thinking of when we were trying to design a deep learning model to listening in a conversational context. And so to us, what we were really going for was an SCT system that listens more like a human. So traditional SCT just kind of like hears sounds and transcribes it with no kind of idea that there's necessarily a conversation going on. And then you usually tack on all of that after the fact with like diarization, and maybe you do some post-processing with an LLM, but there's no kind of real-time conversational understanding of what's being said. And so when we were thinking about like how we designed that system, there were two aspects that we really wanted to capture. The first is we wanted to make sure that we were able to have a model that contextualized what was being said in terms of natural conversational turns. And so that's what Nick talked about, where we're trying to build a model that like views the audio in terms of turns and turn dynamics, so that like all the context is shared across a turn, for example. The second thing that we wanted to do is we wanted to be able to mimic what humans do when they're listening, which allows us to respond in very close to real time, which is basically to think while listening. You usually are kind of like mentally adapting to what you're hearing all the time while I'm talking. And many especially streaming STT models don't do that. They just kind of are like, that was a word, that was a word, that was a word. But they're not really kind of like revising their understanding as more context is coming in. And so that was kind of what we were trying to design a system to do. But many people have been using Nova 3 successfully. And so we had a high bar. We wanted to do this without sacrificing any of the things that people like about traditional Deepgram STT. So namely our accuracy, our concurrency, and the ability for users to boost key terms. If you're on this call and you're not familiar with key term boosting, that is Deepgram's way of telling you that you can sort of provide some priors to the model about words that might be in the transcript, especially if you've got proper nouns that are very important. And then the model will basically learn from those priors to make it more likely to get those words and their spellings and their capitalizations correct. It's a cool feature. If you have not tried it yet, I encourage you to check it out. Also, to those blog posts Nick mentioned, we wrote a blog post about some of the changes we had to make for key term boosting to get it to work in like a real-time streaming context. And so I'd also encourage you to check that out if that's a functionality that's particularly interesting to you. All right, so I can't do the technical side of the talk if I don't share some plots. So let's start with thinking about this first goal, like natural listening. What does it mean to have a natural response time? A lot of you have probably read all these blogs about like natural real-time systems have 100 millisecond responses, but of course humans are much more complicated than that. And so what this plot is showing is we took some of our data and we looked at basically how long humans typically take to respond to something that's being said. And so that's this blue line. And for those of you who are not familiar with these plots, these are kind of like this is a CDF plot. It's kind of like a quantile plot. The way you'd read it is you'd sort of look at 1 second, and up here, this 0.6 would tell you that 60% of human responses occur in a second or less. Whereas like if you go all the way out to 2 seconds, this would tell you that almost 90% of human responses occur in 2 seconds or less. And so this is the general picture. One thing that kind of muddies this picture is that when we did this on all the data, it includes several things that are not as natural, like, or not good turn taking. They're things that humans do, but they're not things that we necessarily want agents to do, like barging in or interrupting. Another thing is that when we looked at these data, a fun fact was that this included meeting data. And in a meeting, when you can see someone, you actually respond to other visual cues that it's your turn to take over the turn. And so you can see that there's like this interesting peak of things that where like humans respond at 0 time. And of course, that's these phenomena at play, barging in, taking the turn for other reasons. This green line, though, is what happens if you take away the 0 time responses. And so you can see that actually, while we want low latency, humans have this like nice spread of responses that's sort of typically in the like 0 to 3 second range, depending on the context of the conversation. And it's a little bit of a spoiler, but when we were evaluating Flux end of turn detection, what we were looking for was a pattern like this, but faster. Why faster? Because for your voice agent pipeline, you need that extra time to be able to orchestrate your LLM and TTS calls and like the extra compute associated with those. And so what I'm showing here in the yellow solid line is the end of turn detection times achieved by Flux with a 0.8 threshold. And you can see that, for example, at the 50th percentile, Flux is typically in the 300 to 500 millisecond region, compared to humans who frequently take like a second to respond. And so this tells you that we kind of like have now built the budget to respond in a natural way. And that's kind of what we're going for with Flux, something that's going to feel natural when you're using it in a conversation. So I said I was going to talk about what we did do, but because, we anticipated these questions and we're getting a lot of them even in this webinar, I thought it's good to talk about what we didn't do. So here's some common solutions that we experimented with but did not quite fit. First of all, a lot of you are asking about VADs. We are not doing any turn detection or turn state modeling based on VADs. And the reason for that is severalfold. First, silence doesn't mean someone's done. The phone number example, which everyone loves, is a good example. If you pause in the middle of your phone number, even for a while, that doesn't mean you're done with your turn. But the second thing is that when you only look at silence to determine if a turn is done, you're missing important acoustic information. If I, for example, say to you, hey, would you like to come to my party on Tuesday? That inflection, which I exaggerated, I don't actually talk like that, fortunately, at the end of my speech kind of like tells you I'm asking you a question and prompting you to respond. And if you're just looking at the silence after someone's done speaking, you miss those important features. And so another example of that is, of course, the semantics. If I just look at the silence, I'm missing what was said, and so I don't have any semantic information. And so you could say, and so that was one thing we were trying to move beyond, but the other thing we were trying to move beyond was like the notion of consistency. You are not someone who's like, I hear someone talking, but I have no idea what they said. If you use a decoupled VAD and STT system, you can get these weird inconsistency where the VAD thinks someone's done talking, but the STT thinks it's still going. And like, what do you do with that? And then you have to orchestrate around it. An all-in-one solution that ignores the VAD aspect is also a more consistent solution. The second thing is we wanted to develop a real-time STT system that was able to like stream in audio and stream out transcripts. And for many people in the industry use transducer models for this. And we actually didn't use transducer models. The reason we didn't use transducer models is that they generally, to get good accuracy, use kind of a fixed look ahead. So they're kind of like looking half a second into the future by the time that they decide a word is done. And the reason that they're doing that is basically to have a little bit of additional context. But the problem with that is that means that you're delayed, right? Like everything is necessarily happening that look ahead slow. And like I said, we wanted to make sure that we were snappy, especially right on end of turn detection. And so transducers didn't work for us. They tended to exhibit worse accuracy and kind of a latency floor that was not quite fast enough to be natural. The other thing which many people do to get around the transducer problem is they use something like Whisper and they have a separate end of turn solution. And then when end of turn fires, then they go and transcribe everything with Whisper. And then they say, great, now I like heard everything with all the context. But the problem with that is that like now you're waiting. There are two things. First of all, you're waiting for your transcript to happen. Like, okay, I've detected end of turn. Okay, now I know what the person said. And that's like a little weird. And it also removes the like nice feedback of the update feature that we tried to build, where you can see how the transcript is evolving. The other thing is, and so you can try to cut that down by like doing like little chunks like Nova 3 used to do. As you kind of saw, we were like updating, like we were kind of like finalizing transcripts frequently for you. That works, but the problem is that then you lose this whole context, right? And humans don't really just like be like, oh, I remember what was said in the last 1 second, but not the context of the whole conversation. So those are some things we didn't do. And so this is an example of kind of like how all these things are working together. I'm doing this weird thing where I'm like showing the plots and then telling you where they come about. So bear with me, please. But this is basically a recording of me using the phone number example. I don't know why I'm over-indexing on the phone number example. I promise that we didn't like put in a bunch of phone number data to make this work. This just popped out of our training. But the phone number example is cool because it's a very natural example. And so in this case, I'm giving a phone number. And you can see from this waveform in blue that I pause for about 1.5 seconds in the middle of my phone number. And the EOT probability remains low. Next 3 digits, EOT probability getting up there. This could be a phone number. Maybe it's a British phone number, which are slightly differently formatted to American phone numbers. Last 4 digits, oh, that was end of turn. That was that they've given their phone number. And so you can see 2 things. First of all, you can see we're not using a VAD because like there's silence here and there's silence here. And the 2 probabilities are different. And so it's not just like we're accumulating probability over the course of silence. Like there really is acoustic and semantic information in here. And then the other thing that you can see is that like we are keeping this full context. Like this at the top is how the transcript is evolving over the course of this example. And you can see that it's like, and well, it's harder to see here. I'll show another example later, but it's effectively growing, and then the end of turn is responding to that as well as the acoustic information. So turn-based context, that was the first thing we wanted to achieve. And so how did we do this? So to understand the flow of conversation, the thing we basically did is we moved from having separate decoupled solutions or a hierarchy of solutions where like end of turn triggers transcription to basically jointly modeling both speech to text. And so this involved designing a new STT architecture that could model EOT using both audio and transcript. So like our EOT probability is a feature of both acoustics and semantics, and that means the silence, the inflection, and the words that have been said. But it's more than that. It's not just like we feed transcripts into an EOT model. It's actually a full model. And so transcription is also informed by the turn state. So for example, if we detect an EOT, that affects the way in which our transcription inference algorithm runs, because we know that at end of turn, you need to finalize your understanding of what the person said. And in particular, we're using a single architecture for both tasks, which means that the context of the conversation is shared between both speech to text and end of turn detection and start of turn detection, but people are more interested usually in end of turn. And so that single architecture means that the model is modeling basically like the entire turn-based context. But of course, everyone likes talking about model architectures, and everyone thinks like, oh, you know, so much of the magic is in like describing the right model architecture. But of course, garbage in, garbage out is a famous saying in machine learning. And a big part of also the Flux work was actually data work. And so developing really high quality data that represented like natural conversations. And so Deepgram, you know, one of the reasons that we're able to put out models in the space is because we have a large proprietary data set of conversations that are highly representative of human turn taking. And we were able to build on those data to come up with a multi-stage training curriculum that allowed us to combine like the large scale pre-training that is usually associated with good, strong STT with kind of a conversational fine tuning that really focused on improving like the model's performance specifically in a conversational context. Cool. So that was the first thing. Like I've said it 1,000 times, but I'll say it again because like I think context is very much the name of the game for how we continue to make models smarter in the like human and voice AI space, but context. So a model that is thinking about the conversation in terms of conversational context. But the other thing I mentioned was this aspect of thinking while listening. And so you kind of saw this in Nick's demo. You saw an example of someone using Flux. I'm now basically going to play back an example to you in slow motion of if you were to like look at the updates in slow motion, what it would look like while Flux was transcribing something you were saying. So I hope this plays. Here we go. You can imagine me saying this, can I please have 1 cheeseburger an order of fries, and I said it faster than that, is the point, and a Diet Coke. Okay. And so the thing that I really wanted to highlight here was that at some point you can, having two play buttons is very confusing. Why did I do that? At some point you can see, yes, can I please have one cheeseburger and order? If you imagine cutting the phrase, hey, can I please have a cheeseburger and an order, and an order and order, those are ambiguous at that point, at the point where you cut the conversation. And so I could be saying, can I please have one cheeseburger and order it to go? There are many things that could happen here. But a little bit later, Flux has revised this to an order. It has changed its understanding of the situation. And that's kind of what I mean. Like, you as a human are doing a similar thing. You're revising your understanding of what has been said, and you're not just like finalizing things constantly. Like, finalizing is this weird concept that applies to speech to text models, but not really to humans. And so this was really like, this was born out of our desire to come up with a system that's thinking while listening. And the real motivation there is that, like, you want to be constantly like taking in more context and understanding more of the conversation, but you also basically need to be ready at end of turn, because you don't want to like go back and then understand the context after the fact. Like, you need to be ready when it counts. And so the way that we achieved this is we developed a novel inference algorithm that we didn't think about it this way at the time, but after the fact, it has some analogy to test time scaling for LLMs. So if you're someone who's more familiar with LLMs, there's recently been an idea, in the past year or so, there's been an observation in the literature that by kind of encouraging LLMs to generate more, like making them think, depending on how much you want to anthropomorphize, these models are able to achieve better performance. They're basically able to kind of like test out more routes in their answer space and come up with an answer that is more likely to be correct than if you just tell them, like, give me the answer immediately. And so we came up with basically a comparable inference algorithm for STT models that allows them to continue to think about the transcript all the way until the end of turn is detected. And so this generates a working transcript, and the only real finalization point is at end of turn. But that's fine, because that's the only point at which you need to have like committed mentally to what someone has said. If you're familiar with test time scaling, you also know that it's probably expensive. And one of the things about Flux is it's not just a research. We didn't just put some research innovation into this, but it was also very much like a research and engineering co-effort. In particular, to sort of amortize the cost of this potentially expensive new inference algorithm that we developed, we actually developed some custom CUDA kernels. And so when you're running our models, you're running like our in-house proprietary kernels that are designed to accelerate like the test time compute without adding latency. And so that's why we're able to like balance both like high performance and low latency, is basically like by building infrastructure that is optimized to running these models in-house. One thing that I want to mention for like the interested community here, though, is that this is only really a partial solution to thinking while listening. And the reason it's only a partial solution is because right now we're only focused on the STT layer. And one of the things that you're doing when you're thinking is you're not just thinking about what the person's saying to you, but you're also thinking about how you're going to respond. And I think that this is a really interesting challenge for the voice agent community, is like, especially as we're working with, decoupled models and everything, how do we build things that mimic that process? Like, you think of your response ahead of time rather than just like wait, like, again, right now voice agents are waiting for someone to be finished, then they're generating their entire response and then responding. And so that like breaks the naturalness, right? And it breaks the naturalness mostly for latency reasons. Like, you have to wait this entire time to think of what you'd like to do. And so the question is, how do we do that? And this is something we're very actively thinking about at Deepgram Research. But for the moment, from just the STT layer, that was the motivation behind the eager end of turn events that Nick talked about earlier. The idea is that if you sign up for it, this is not enabled by default, but if you specify an eager EOT threshold, we will send you these kind of like triggers of like the person might be done soon. Like, we think this is maybe a good point to think about your response. And that allows you to get this jump on your LLM response. And so while not do it perfectly in the way that all people who work on end-to-end deep learning like me love, it gives you a way to kind of like mock up like, oh, thinking while listening. Again, this is not quite human-like, because like in this paradigm, the idea is that if we send you turn resumed, then you're probably going to have to recompute your response again, depending on your pipeline. So it's not quite human-like, because if you keep going when I thought you were going to stop. I don't just like forget everything I thought about to that point. That would be crazy. But again, it's still, computers. We should never. I'm an ex-physicist. I like this quote by Richard Feynman, which is like, we should never turn into birds who are arguing about whether planes are flying. Planes are definitely flying, even if they're not flying the way birds think they are. And so this is similar. It's like, okay, that might not be exactly the way human works, but it's like, we think a very good proxy in the voice AI space for generating that natural real-time conversation. And so, as I mentioned, part of enabling some of this thinking while listening was custom development of several custom CUDA kernels. For the sake of those who are kind of interested in this, we've given this example of kind of like what one of those custom CUDA kernels might look like, specifically for the case of attention, because many people are familiar with the process of a KV cache and attention. And one of the things about a KV cache is that generally you have this approach where basically like, as you process data sequentially, you build up a KV cache. And that's obviously not what we're doing here, because like Flux is not just going to build up this infinite length KV cache. And so one of the things that we frequently have to do is we frequently want to be kind of like manipulating and computing over partial parts of the cache based on how our infrastructure works. And so if you were to do this in native torch, the way you'd naively do it is you take your cache, you'd extract the part of it you wanted, you'd do attention, and then you'd get rid of the parts of it you don't want, and then you'd base your results on that. And we don't want to do this. There are two expensive steps in this. First of all, the masking. Computing over everything and then masking things out is inefficient. PyTorch does this not because it's stupid, but because it's flexible. It wants to handle all cases. In our case, we don't need to do that. And so we found a way to get rid of that step. And then the other thing is this like extracting of the part of the cache you want. This can be a very expensive operation because you're like pulling out everything into a new tensor that you are only going to look at that part of the tensor. Like, but that's silly. The numbers are there. They are somewhere in the machine's memory, and you just need to access those numbers. And so we were able to come up with this like kernel that kind of fused all of these operations together into a more efficient pipeline, well built for our inference algorithm. And so, there have been a lot of questions about like, what's the future? Let me say it. We have heard you. Multilingual. We are thinking very hard about multilingual. We really want to make sure that we get this right, not just in terms of porting over English and giving something, that's a half-baked copy of English, which is more and more the trend in SDT. We really want to get this right because conversational dynamics are very different across languages. People pause for different amounts of time. People use different inflections. So it's very important for us to like take the time to get that right. And so we know you're anxious for it. We are working very hard on it. Thank you for your patience. The other thing is we're working really hard on increased context. One thing people have pointed out some things about like, oh, well, my agent said, is your name Jack? And the person said yes, and end of turn took a little bit of time to fire. The reason that end of turn took a little bit of time to fire is because we don't know your agent said, is your name Jack? Right? Like, yeah, end of turn should be snappy in that case. But when we're only listening to one side of the conversation, I did this interesting data analysis where I looked at how many turns in a specific data set started with the word yes, and it was 50%. When you're testing and you're saying yes and you want snappy end of turn, you think yes is definitively a turn, but actually across the data, it's not. 50% of the time someone says yes. And by the way, I'd also like to talk about like yes on its own is very ambiguous. And so we're thinking of ways that we can basically increase the context. We're thinking of what's a good API design to be able to get context from voice agent developers so that we can, better improve the context that's being fed to the SDT layer and improve both end of turn and things like back channel detection. And then the other thing is selective listening. One of the very complicated, selective listening is a complicated problem. And we can all express it in natural language. Just listen to what I want you to listen to. But the problem is when you try to write that down in like a mathematical formulation, it's not as simple as that. And so, different people have opinions of like who the primary speaker is, what speech should be captured. And so we're basically trying to think about like how we generalize this to something that's going to work across our broad developer base. Again, we work with developers like you, not with customers. With customers, you can just say, this is my definition. When you're working in a B2B setting, it's really hard to find a generalized approach to all that. So that's the big stuff. That's the fun research stuff that we're working on that we hope to have something to share on, towards the end of this year, beginning of next year, but we're also aware of just kind of like general feature improvements. And so some of the things we're working hard on at the moment are like very good word times. We know a lot of people care about word times, and so we're trying to add that. I'll point out that like, there's certain things that we have not prioritized for the original version of Flux, word times, formatting. We're working on these things. I will point out to you though that humans like it. Your LLM doesn't need it. LLMs are very good formatters, and they have a great understanding of text without word times associated. That's why it wasn't an initial priority, but we are hard at work on it now. Rest assured for those of you where your use case needs it. Then the other is on-the-fly configurability, particularly for key terms. The ability for you to update your conversational priors, your end-of-turn thresholds, your key terms as the conversation evolves. We're hard at work on improving our inference algorithm and our API to be able to be flexible to that. So I am as I frequently tell people, I have never once been accused of concision. So I'm trying to stay to time so that I don't stress out our wonderful organizers who risked putting a researcher in front of all of you lovely people. And so I am going to kind of try to take it home by saying, a lot of you also have really excellent questions about like wanting to try it, wanting to talk with our team, can we is it HIPAA compliant, stuff like that, all great questions. As you can probably guess, I'm not the expert to answer them, but we have plenty of resources for you. We have access to the demo. We have ways for you to contact us. We are very used to working with developers like yourselves. Please reach out to us. We are constantly working on improving on our docs. Please use our docs. Please provide us feedback. Anything we can do to help you, help make Flux awesome for your use case. That's what we want. So that's all that I had in terms of material. I think that now there are a lot of questions that I think we'd like to go through. I think I'm going to bring Nick back up on stage with me, and we can kind of start flipping through some of those. Sound good?
Yeah, let's do it. I think maybe let's just go top to bottom by upvotes. I know we answered a bunch of these while this was going on, but I think maybe we just go through from top to bottom. So the first question on top, 23 upvotes. Can Flux detect custom emotions in real time? So frustrated, angry, sarcastic. It cannot at the current moment, but this is definitely something that we've heard from a number of customers and definitely something we're thinking deeply about. And more so than just detecting sentiment and emotion in this context out fashion, but a number of other things like identifying like other sounds that are happening in the environment and identifying DTMF tones, things like that, along with selective listening and that primary speaker identification stuff that Jack.
And if I can just point in another reason this is hard from the research perspective is that like, I think of the world in terms of observables and latent variables, and emotions are latent. They are not actually like, we think of them because we talk about them all the time, and humans seem to have parts of our brains wired to understand certain emotions within humans, but emotions are latent in the sense that they are not really a well-defined thing. And so from like a modeling perspective, it's very hard to say like, oh, this is angry for everybody. Oh, especially when people are like, I want both frustrated and angry. I don't know about you, but I have a small child and I'm frequently frustrated and angry at the same time. Like a new set of emotions that come out as a parent. I'm also happy a lot too. But so that's another thing, a lot of these things, it's like we want to build it, but we build for a lot of developers. And so it's hard to define it in such a way that we, make everybody happy. And so we prefer to take our time with those things. But feedback always helpful. The more explicit you can be about what things mean for your use case, the more we have to work with.
Awesome. Okay, so going down the list, the next question was, when will Flux be supported on the EU endpoint? It is supported today already on the EU endpoint. I believe that is publicly accessible and it's no longer behind like a request form. But I don't know, Hassan, maybe you can answer that more specifically. Next up, is there a roadmap of following languages that will come soon? Jack kind of mentioned this already. We are hard at work expanding with additional languages. It is not as simple as perhaps expanding traditional speech-to-text languages because we are also modeling end-of-turn probabilities as well within this model. So we're trying to do it right. But of course, we have heard this from many, many customers. And so it is top priority. Why not change something new with different voices? So we're focused on more of the STT side today in this webinar, and me especially. But we are working on many exciting things on the TTS side as well. maybe we'll have a TTS webinar coming up soon. And that the next question was around compliance. So yes, we are HIPAA compliant and a number of other industry compliance certifications. I've posted a link there that you can see all the details on that.
We also have self-hosted offerings. You need air gapping solutions.
This question was about a specific error. This is unexpected, so please reach out to us. I think the best way to get a quicker answer would be to provide more information on in GitHub discussions. We have a Slack channel that does all pipe straight through to our team. So if you guys can share more details there, we can take a look at that. Unfortunately, we cannot extend pricing beyond October, but if you sign up for a new account, you get $200 in free credits. So hopefully make use of that if you haven't already. Also, there's a couple days left in October, so there's still time. Yeah, we do have self-hosted support. That was the next question. The next question was, in the context of a phone call, can Flux filter out background conversation, i.e. while walking on a street or sitting inside a chatty office, and reliably identify conversation with the actual caller? Jack, why don't you take this one? I've been talking a lot.
Yeah, so I sort of mentioned this in the context of selective listening. We actually do think that this is, like, our internal research, I'll tell you, like, we think that this is feasible. The problem is, again, background conversation is something that is well-defined for your use case, but not globally well-defined. So locally well-defined, not globally well-defined. For example, there are many customers who actually come to us and they're like, we want to know its background, but we also want to know what was said. You know, like, for example, in a natural conversation, if you are working at a drive-through window and the person talks to their kids, says like, did you want a hamburger or a cheeseburger? And the kid goes, cheeseburger! And they go, cheeseburger, right? Like, actually, there was a clearer cheeseburger there, which was the kid shouting cheeseburger, than like what was relayed to you. And so the problem is that, like, most customers don't just want complete noise cancellation, get rid of the background entirely. They want something contextual that more accurately reflects what a human would hear. Again, difficult. Flux is admittedly currently designed for a primary use case of like listening to an intended target speaker. We're thinking about how to expand other use cases. I'll throw it out there. Because we were very interested in achieving parity with Nova 3 SDT, I will say that, like, we actually tested it across a variety of domains and in multi-speaker environments. And, you know, for my best estimate, having also played a major role in Nova 3, it holds up pretty well as just a pure transcription model. It's more just sort of like you have to be careful of interpreting the outputs in your specific context. So all that to say, selective listening on the roadmap, thinking about how we can do it the best way for developers. Love feedback about what it means to you. If you want to just use it as a transcription model, you know, you can probably do that. I was a little off topic, but hits on some other questions. What do we got next? I know something refreshed, and now I like.
Yeah, it's weird.
Oh yeah. What languages? I think we've covered that. Other languages to follow. Business questions, not for me. Currently, I have signed up for $200 credit that I've been using for Nova 3. Will that same credit be used for Flux? Nick, that's a question for you.
Yep. Your free credits apply to all products.
And we have a question.
I was going to say, Nick, there's a question from Anurag. How is this better than OpenAI's real-time API that supports VAD plus speech-to-speech models? Latency could be super low. Any thoughts there?
Jack, you want to start?
Yeah. So I think we mentioned the VAD.
Big question.
Yeah, it's a big question, and you know, I think one of the things that's been most amazing about this launch is just seeing the wide range of use cases that people are putting it to. Speech-to-speech models, though, are speech-to-speech models is a big other topic, and so we can have another webinar maybe where I can share my thoughts on them, though you'd all be bored to tears. But one of the things I'd say is, in short, like, and we wrote some of this in our blogs, but like we really like the idea of speech-to-speech models. We see it as the future for like high naturalness, but it has some shortcomings right now. First of all, they're not particularly good rule followers, and that's basically because there's just not a lot of data to teach them how to follow instructions, right? Like there's not a lot of data of you being instructed to do something verbally in a speech-to-speech context before you do it. And so for many of the people we've talked to who've tried to use them for business use cases have found it really hard to get them to like obey the only thing you really care about, which is that like, yeah, we love naturalness and everything, but you got to follow the business logic. If you have a very natural agent that goes, sure, I'll issue you a $5,000 refund because you didn't like the taste of our ketchup, this is a problem. And so one problem about speech-to-speech models is they're very natural, but they don't follow rules. The second thing is, we're working with developers, and you guys are constantly like, a lot of this work is like not just like is taking a 90% solution to 100%, right? And like debugging edge cases and interpretability and like control, and that's kind of what we wanted to offer here. And so one of the other things is like, yeah, you can get super low latency. I can get super low latency with a TTS model. I'll just respond, I don't know how to answer that every single time you ask me anything, right? Super low latency, not very useful. And so, I think that, yes, speech-to-speech models are very promising for the future, but we felt that this was the right step towards that right now by still offering debuggability, interpretability, controllability, things that seem very important for this world where generative AI is not so perfectly refined that it can just do everything yet. Do you have stuff to add, Nick?
No, I think you covered it pretty well. I think one, it's that hallucination, end-to-end black box sort of thing. Like you end up running into a bunch of edge cases and problems that you didn't expect. And you also have no observability onto that and where the problem went wrong within the system. And so while speech-to-speech models are great for emotional representation and keeping context throughout the flow, you really, for a production grade solution, we've seen that today they're just not there yet. Maybe in a couple of years. We are working on that as well.
Yeah, I have a question in the section of the queue that I really want to take because I think this is very important for people because it is something we are noticing too. So Stu Kennedy has pointed out, are you going to put in the capability to identify back channel speech or other speaker speech so that speech started gets way less false positives? And he makes the point that TTS models are getting more realistic and users are starting to interact more naturally, which is really cool. Like people are starting to back channel the bots, right? Like that's a very interesting phenomenon and awesome from a modeling perspective. One thing that I will point out, though, is that like from the STT layer on its own, very frequently what you're seeing are not, in some sense, false positives. Like a back channel is an utterance. And again, it is information. Like if someone's saying to you, that is not something you just want to throw away. It is context for understanding how they're feeling about what you're saying to them. So that's one thing. One thing is that like we right now went for a solution where we pass you everything we hear like you hear everything. We understand, though, that means that if you, for really sophisticated use cases, if that means you always interrupt your agent on speech started, this can be problematic. This brings me to the other part of the equation, though, which is that it goes back to this more context thing. Right now, if you're just using the Flux layer, we don't know when you're speaking. And so, like, if I go, yeah, was that a back channel? Well, if you were talking to me, it was certainly a back channel, and I was nodding and agreeing with you. If you said, like, did you have a good day? And I went, yeah, that's not a back channel. And so while there are subtle acoustic differences and subtle wording differences for back channeling, the big feature is missing. Are you talking right now? And so again, this in our mind falls under like we have thought about, we actually thought very heavily about just shipping you a solution that's sort of like, yeah, this is maybe a back channel. But we weren't convinced that it was like an 80% solution that readily led to a 100% solution because of the importance of context and doing it right. And so, yes, we are very interested in putting in this capability. We think it will unlock so many awesome natural interactions, but just be aware that kind of like that's one of the things we're struggling with from like a pure STT product.
Awesome.
Been having this issue where Flux will not transcribe the word PPF correctly. Okay.
Yeah, I mean, I would say try out key term prompting for something like this.
They did say key term prompting. Yeah, I'll point out they say key term prompting works amazingly well with Nova 3. It's not working for this use case in Flux. If key term prompting isn't working for you at all for any key terms, definitely contact us. It's working in our testing, and so that would tell us that we might be doing, we might have miscommunicated something in our API docs or something like that. One thing that I'll point out about like key term prompting in real time is it's harder, right? Like if I say pirates, you hear pirates. If I say of the Caribbean, right? Like if you're trying to get that live, going back and realizing that like an entire keyword was coming in real time is harder. And so definitely we do not necessarily, like we do expect discrepancies between the key terms captured by Flux and the key terms captured by Nova 3. It's not exactly one-to-one, though we've seen that in aggregate, the performance is very similar. That said, PPF, I don't, like, I wish I had a better answer for you other than, statistics are crazy. And all the time we're working with statistical models, in spite of the fact that people think of STT as just like a discriminative model, like STT is ambiguous. And so I'm sorry to this happening. We encourage you to continue trying key terms. If you see evidence key terms is not working for you at all, reach out to us. Other than that, though, we do offer custom models if things are very important to your use case. We do work on domain models, as I mentioned in the thread. And so, hopefully there will be something here. And then the other thing is just remember, like, depending on your use case, there might be things that your LLM is robust to, right? Like, worst comes to worst, you can always consider something like, by the way, if you hear this thing, it probably means they meant to say PPF because you're absorbing text from an STT system that is, has statistical imperfections. So,
yeah, I'll also add this, like, while we have key term prompting as a solution for getting these entities in like specific terms right in a more accurate way, this is still something where like key term prompting is limited, right, to 100 key terms. So this is still something we're thinking deeply about in the like, how can we make the greenfield open space when you don't know the names that are going to get said? How can we improve the accuracy of the names that get said? And so this is something that we are continuing to think deeply about and making it easy for you to either do your fuzzy matching downstream or provide more context to the model to make this more accurate in more ways than just key term prompting. And then generally, I would say in terms of, I guess you mentioned reaching out in the Discord and GitHub communities, but for other folks who are having issues, please reach out to us in Discord or in our GitHub discussion section. I've sent the link in the chat. We have an internal Slack channel where all of these things pipe through to. I'm in there responding. A bunch of other folks are in there responding. And so that's a great way to give us feedback and ask questions.
I somehow didn't notice we were a quarter of the way through the list. We have a way to, I think a lot of these questions, hopefully we've answered through other questions. We have a way to, I've been told by people who are much better at this than I am, that we have a way to export these questions and follow up on the ones where we can really help. In 1 minute, I want to go rogue and just hit a couple of others because I've seen a couple of important ones. Is that okay with you, Nick?
Yeah, go for it.
Awesome. So one that's coming up is I'm building Flux through like PipeCat or VAPI or some other intermediate bundled solution, and we're finding like duplicate end of turns between like their end of turn detection, our end of turn detection, or their the VAD based solution and the. I want to emphasize this. We designed this to be used independently. Similarly, I've had questions about like how end of turn timeout threshold affects like the end of turn probability threshold. And the answer is it doesn't. There is no, like, we are really trying to use, like, we are not using a VAD in the model, and we're trying to use anything that's like a timeout as little as possible. And so to the extent possible, our perspective, obviously it would be our perspective, but to the extent possible, our perspective would be like, turn off the other solutions, rely on Flux. Particularly, I don't know if that's what our partners are always saying, but that would admittedly be our perspective. Our partners are doing a great job with Flux. It's just that like it can be like I said about consistency, it can be confusing if you get multiple opinions from multiple places. And so, all in one is what we're going for. Let's see. Words that look similar. What is the accuracy of language identification under clean speech? I'm going to skip that because, as I mentioned, multilingual is on the roadmap. We're not necessarily doing language identification at the moment. What is the model name? Flux General EN. Is that correct, Nick?
Yeah. Flux General EN.
I, of course, like all researchers, hit it from an entirely different endpoint, so I have no idea.
Yeah, that's one thing that some customers have had questions about. Is it's a different like param split up than Nova 3 in our former models, where we had a model param and a separate language param. We've now combined that, so the paradigm is model equals like model name, use case, language.
Yeah.
So Flux General English.
Another great question really quickly is that someone is saying, Min is saying that the phone, like if someone gives a phone number right away with long pauses, then the end of turn detection can get confused and might fire preemptively. Yeah, this doesn't surprise me. Again, and Min clearly is aware of this. It goes with the fact that we're only listening to one side of the conversation. And if a number comes out of nowhere, 123, is this a phone number? Like, we have no context for that. Is there a way to help feed in the agent? Yeah, we're actively thinking of that. Maybe that's what we will ask people for.
I would also
I could go on forever, but probably shouldn't. So.
Well, real quick to one of your last points, Jack. One of the things I would also really recommend for you guys is to try out different combinations of your EOT threshold, eager EOT threshold, timeout milliseconds. Experiment with what works best for your use case. Because while we did pick a default of 0.7 for EOT threshold, it really depends on what you're building, what is best for you. So, yeah, and I think we are over time now. This has been great. Thank you guys all so much for joining. I believe we'll be sending out the recording of this presentation after the fact. And maybe Hassan, you can answer if we're sending out additional resources, or you can grab the links from the resources section right now, or use Google to find things like a normal person.
And also, thank you for being here. Thank you for spending an hour of your time with us. Thank you for jumping on early. Thank you for all the great questions. Like, we love this sort of engagement. It is really like the awesome part of being part of this community right now. And so, like, yeah, I had a great time doing this. I think, that's Nick's emotional barometer, but he had a great time doing it too. So,
Yeah, and I'll just add, if we didn't get to your question, we will try. We'll be downloading all the questions and trying to get to every single question and get you guys answers.
Awesome.
All right.
Well, thank you guys all so much.
That's bye from us. Thank you.